Hi everyone, in this video we're going to be talking about trigonometric equations, so equations that involve trig functions. Here are some steps we're going to follow throughout various examples. So the first thing you want to do is decide with the equation you're given, is it linear or quadratic? Linear, meaning that the degree is 1 for your variable, or in this case your trig function. Quadratic, the degree is 2, so it would look like something squared. Maybe like tangent of theta squared or something like that. If only one trig function is present, you're going to solve your equation for that function. So let's say you only see tangent theta in an equation, you would isolate that expression, tangent theta. You would get that alone to solve for theta. If more than one trig function is present, you're going to rearrange your equation so that one side equals 0. So you'll do a combination of maybe adding or subtracting terms, possibly dividing out numbers to get one side of the equation to be 0. Then you try to factor and set each factor equal to 0 to solve. Now if you can't factor, so if the equation is quadratic but not factorable, well, you can use your quadratic formula. And then if this is the case, you do want to still check your answers that they are in the desired interval. So most of the problems you're going to be given are going to also include an interval that the answers should lie in. And then also we might have to use some identities. So some of our previously learned identities from chapter 5 material, we might have to use them to change the form of the equation. And it might be helpful also to square both sides of an equation. But if you ever square both sides of an equation and solve for a variable, you have to actually do this checking. It's required because through no fault of your work could be 100% right, but you might have what's called an extraneous solution just because you squared an equation that didn't used to be squared. Let's start this example here. So solve 2 sine theta plus 1 equals 0 over the interval from 0 to 360 degrees. So this is just one full rotation on our unit circle. Notice this is a trig equation. There's an equation because there's an equal sign, and there's a trig function inside our equation. So this is what it is to be a trig equation. There's only one trig function in this equation, so we're going to do our first bullet point that we just mentioned, which is solve for that function. So let's start by moving over the 1 by subtracting it, and then divide out the 2, and now notice your sine theta, your trig function, is solved for. Then you just need to find theta. So you're almost there, we just need to figure out what is theta. Okay, so we know that sine theta is negative 1/2, and sine is negative in quadrants 3 and 4. So we're going to use our reference angle of 30 because we know that sine of 30 equals 1/2. And so in quadrants 3 and 4, a reference angle of 30 would put us at 330 degrees. Notice our sine value is negative 1/2. And then in quadrant 3, the reference angle of 30 would give us 210, where sine is also negative 1/2. So our solution set, we're just going to use these squiggly angled, these squiggly braces, and that means our solution set, and it contains two solutions. So theta is 210 degrees and 330 degrees. Now I do want to mention that you can use your inverse trig functions here. So let me show you what happens with that. So sine theta equal to negative 1/2 is what we figured out from up here, which would let us know that theta is sine inverse of negative 1/2. Now, we have to be careful if we do choose to use our inverse trig functions instead of just our regular reference angle back here, because inverse trig functions have a limited range based on how we came up with them from their limited domains that we restricted initially. So inverse sine is only defined in quadrants 1 and 4. So if I use sine inverse to figure out my angle theta, it would only give me this angle in quadrant 4. It wouldn't actually give me this other angle that I need for angles between 0 and 360. So then in quadrant 4, I can go ahead and use sine inverse, let's say on my calculator, of negative 1/2, and in degree mode it would give me negative 30, because it's always going to give you a negative angle in quadrant 4 to make it continuous, coming from negative pi over 2 or negative 90 all the way up through 90 or pi over 2. So then you would just add 360 and get your positive angle of 330. And so in order to get this missing answer, if you use sine inverse, you have to actually consider the reference angle here. So if your calculator gives you -30, that's letting you know that the reference angle is 30 degrees. 30 degrees between the x-axis and your actual angle. And so you can use that fact to give you an angle in quadrant 3. Take 180 and then add the reference angle of 30 to get 210. Now, same example, but notice the difference. Find all solutions. So if your equation doesn't come with an interval, or if it specifically says find all solutions, you have to just add multiples of the period of the function. So here's what that looks like. So to find all solutions, add integer multiples of the period of sine, and this is going to be found to the answer from part A. So think about it real quick. Think about your sine function, and hopefully you remember the period for that is 2 pi radians, or in this case 360 degrees, since we're in degree mode. So we just take our two answers from part A, 210 degrees, and add multiples of 360, where n is an integer. So an integer just means it's a whole number, but positive or negative. So like plus, this is plus 1 times 360, plus 2 times 360, plus -1 times 360, and so on. So this would give you every single multiple around your unit circle that would be coterminal to 210 degrees. Same thing, you add 360 times n to your other answer, 330, and this is all the solutions. And then usually we just include this little statement to let whoever's looking know that n represents an integer. Let's try this next example. Solve sine theta times tangent theta equals sine theta over the interval from 0 to 360. Now notice this time we have more than one trig function present in our equation. So this is the bullet point we mentioned where we're going to make one side of this equation equals 0. And in this case, we just do that by subtracting sine theta to the left side. Well, technically from both sides. Now, what you want to try next is to factor if possible, and you can. Two terms in your equation both share a sine theta, so you take that out of both terms. And the reason we want this to be 0 and factored is because of this very nice property that we have. If two factors or any combination of factors equals 0, when you multiply them, we know that by the zero product property, one of the factors had to equal 0. So sine theta is 0, or tangent theta minus 1 is 0, making tangent theta equal to 1. So we know on our unit circle from 0 to 360, at 0 degrees and 180 degrees, sine theta is 0. And then we also know on our unit circle that at 45 degrees and 225 degrees, we would get a tangent value of 1. And so our solution set is all four of these answers, because all four of these answers satisfy our given equation, and they're in this interval from 0 to 360. And if you're ever not sure, you can plug them back into your original equation to see if it's equal, if you want to check. Okay, so just a caution when you're working on problems like this example, if we were to have divided the sine theta at the beginning, it would have only gave us two answers and we would have missed the other two. So the missing solutions are the ones that make the divisor 0, and for this reason you want to avoid dividing by an expression that has your variable in it. So that was back at the first step. This sine theta, if we divided both sides by sine theta, which is tempting, we would have just got right here. We would have got to right back here, which was tangent theta equaled 1. And we would have missed this whole sine theta equals 0. So when you can, avoid dividing by a term that has your variable in it, which in this case your variable was theta. Next example, solve tangent squared x plus tangent x minus 2 equals 0 over this interval 0 to 2 pi. So this interval is still one full rotation on our unit circle. It just happens to be in radian measure. Okay. So what I want you to notice is you have the same trig function multiple times in this equation, but it is squared, so this is a quadratic equation. Okay, so we're still going to try to factor if possible. Alright, so if it helps, rewrite your trig function with a different letter if you want. You can think of this as y squared plus y minus 2 equals 0. And that might help you see the factoring. It's just y minus 1 times y plus 2. And so this does require that you remember some of your factoring techniques. You can use the AC method or whichever way, snowflake method I know people have learned, or the box method, whichever way you know to factor a quadratic equation. Once you have this factored and we know that it equals 0, we set each factor equal to 0 using our zero product property, and then we solve for our trig function. So tangent x is 1 or tangent x is -2. So let's start with tangent x equals 1. Tangent x is 1 at pi over 4 and 5 pi over 4, and that's in our one full rotation of our unit circle between 0 and 2 pi. So those are two of our answers, but now let's see what happens with tangent x equal to -2. Okay, tangent x is -2 lets us know that x is either in quadrant 2 or 4 because tangent was negative. Tangent is negative in those two quadrants. And so inverse tangent, if you remember when we went over inverse functions, is only defined in quadrants 1 and 4. So notice we'll be able to get a value for quadrant 4 using inverse tangent, but it's going to make us end up missing this value from quadrant 2. So we'll address that. So tangent inverse, I know that if I want to find x, I use tangent inverse. So tangent inverse of -2 is about -1.1. And that value is going to be in quadrant 4 because when you type in tangent inverse into your calculator, it's going to only spit out answers in quadrant 1 or 4, and if it's negative, it's from quadrant 4. Okay, so we need to get our missing value from quadrant 2. Since we want solutions over the interval from 0 to 2 pi, we're going to add pi to our answer we just got, tangent inverse, and that's going to take your answer from quadrant 4 across your unit circle to quadrant 2. Okay, like a straight line across into quadrant 2. Now we actually also need to rewrite this answer, -1.1, because technically that's not between 0 and 2 pi. If it helps, 2 pi is about 6.2, 6.3. So -1.1 is not in between 0 and 6.3. So you have to end up adding 2 pi just to make that a positive value in quadrant 4. So here's what it's looking like. When you type in your calculator tangent inverse of -2, it's going to give you this angle in quadrant 4, -1.1, but we have to get an angle in quadrant 2. So that's where the adding pi comes in. When you add pi, it's going to take you around half of your circle and give you a value in quadrant 2. So that was one of our answers. The second answer, we actually just have to translate this -1.1, because that's technically clockwise, an angle going clockwise here, into a positive angle, which would be counterclockwise. So if we add 2 pi, that would take us fully around our circle until we land back here, and it would be the same, the value would be 5.17. So our solution set was our previous two exact value answers, and then these two approximate answers using tangent inverse on our calculator. Now in this example, we are going to find all solutions of cotangent x times cotangent x plus 3 equals 1, and then write our solution set. Okay, so we have the same trig function present twice, but if you distribute, it's actually squared, so it's a quadratic equation. So we're going to end up trying to factor this if possible, and you can try it. Think of this as a variable on its own. You can say something like y squared plus 3y minus 1, and you can try to factor it. And then if you remember from our bullet points of possible steps, if it doesn't factor, you're going to use your quadratic formula. And this one doesn't actually factor very nicely. And so we're going to use our quadratic formula, where a is the coefficient on the squared term. So there's 1 cotangent squared x here, so that's why a is 1. B is the coefficient on the linear term, on the cotangent x, so that's why b is 3. And then c is the constant, -1. And so you're going to fill those into your quadratic formula, and then your variable is not just x, it's this cotangent x. You have to keep cotangent with it, because it was cotangent x as the linear term and cotangent squared x as the quadratic term. So here's your quadratic formula, and we just fill in 3 for b, 1 for a, and -1 for c. And then you can simplify, and after you simplify a little bit, this is negative 3 plus and minus root 13 over 2. Okay? So that's approximately, if you separate these answers with the plus and minus, negative 3.3 and then 0.3. But notice that's still cotangent x, it's not x. So we still have to find just x based on this being cotangent x. So we know what cotangent x is approximately equal to, these two values. So we're going to use cotangent inverse to find x. So x is approximately cotangent inverse of our two values we found using our quadratic formula. And so x, if we're going to use our calculator, we need to use our tangent inverse button. Most calculators don't have a cotangent inverse button. And so cotangent is reciprocal of tangent. So if I want to type this in, I'm going to type in tangent inverse of the reciprocal value. Now notice this answer has a plus pi. That's because tangent inverse, if it's negative, it's going to give me a value in quadrant 4. So this would be a value in quadrant 4. But we're using this to find cotangent inverse, and cotangent is negative in quadrant 2. So I take this answer, this is in the quadrant 4, and I add pi to it to get an answer in quadrant 2 because we're working with cotangent. And then this one is positive in quadrant 1, which cotangent is also positive in quadrant 1, so we don't have to change anything here. Now to have an exact value and to not have to type in these decimals all the time, I'm going to go back and use the exact number that we got already. So this is 1 over officially negative 3 minus root 13 over 2, and then 1 over negative 3 plus root 13 over 2. So I'm just using the exact values that we found instead of the decimals. And then to make it look a little bit nicer, this is just the reciprocal, so I can just flip this over and put the 2 on top. And then using those exact values in my calculator, I get x is approximately 2.84 and x is approximately 1.27. The question was to find all solutions, so we're going to add integer multiples of the period of tangent, and which is pi. So the period of tangent and cotangent is pi. And so we take our two answers and we add n times pi to our answers. And then we just specify that n is an integer. And that's our solution set. Next example, we're going to solve tangent x plus square root 3 equals secant x over the interval from 0 to 2 pi. Okay, notice we have two different trig functions we're working with here. Now this one's a little tricky, and you kind of have to think about where you want to go with this, and that's why I wanted to show you this example. Nothing is really very clear at the beginning that you should square both sides unless you're thinking about identities that you know. So we are going to end up using a Pythagorean identity here, and that's why we introduced the square here. So I could have brought over a secant to the left, like by subtracting, but the best thing we can do here is actually square both sides. Now on the left, we're going to end up having to FOIL. And so if you want to pause this, you can, and FOIL out the left side. You have a binomial times itself. Okay, you ended up getting, hopefully, tangent squared x plus 2 root 3 tangent x plus 3. And the right side was still secant squared. Okay. All right, here's why we wanted to square both sides. Because tangent squared is related to secant squared by our Pythagorean identity. So we sort of had to think ahead, how is secant related to tangent? And this is how. By the Pythagorean identity, 1 plus tangent squared x is secant squared x. So we replace it so that our entire equation only contains tangent x. Right. Now we start simplifying, and so if you subtract 3 plus tangent squared x from both sides, or 3 plus tangent x, this left side, and then you subtract it from the right side, 1 minus 3 is the negative 2, and the tangent squared x minus itself went away, it was 0. Okay. And so solving for tangent x, you divide by 2 square root 3 and simplify and rationalize. So we know that tangent x is negative root 3 over 3, and then we have to think about, well, what is x on our unit circle from 0 to 2 pi if the tangent value of x is negative root 3 over 3. And so those two places on our unit circle would be 5 pi over 6 and 11 pi over 6. Now, because we squared both sides of our equation, we actually have to check. It is going to be required because of the process of squaring. We might have an extra answer that isn't going to check out. So let's try our answers one at a time. 5 pi over 6, plug it in for x into your original equation, and decide after you work this out, is it true? So you're questioning it until you decide, yes, it's true or not. So tangent of 5 pi over 6 is negative root 3 over 3. Secant of 5 pi over 6 is negative 2 root 3 over 3. And when you simplify this left side, what you'll find is these are not equal. The left side is positive, the right side is negative, and so we consider this 5 pi over 6 to be an extraneous solution. We got it in our work, but it didn't check out because of the process we used of squaring. So let's try our next answer. 11 pi over 6, plug it in for x. Tangent is going to be negative root 3 over 3. Secant of 11 pi over 6 is positive root 3 over 3. And now this is equal. So 11 pi over 6 is a solution. So we actually only had one solution that worked here. So that's our solution set. Now we're going to continue doing trig equations. It's just a second section in your book, so trig equations part 2. So let's try this example. Solve 2 sine of x over 2 equal to 1, and two parts, over an interval from 0 to 2 pi, so one rotation of your unit circle, and then separately for all possible solutions. Okay, so why this is a second or separate section, 6.3, is because you're dealing with different types of angle values now. In this case, this is a half angle. So x is your angle, but you're dealing with half of it. So from 0 to 2 pi, your given interval here, that's for x, that's for your variable. And what you have to do is adjust that for whatever you're given. So we're actually given sine of x over 2. So you're going to place x over 2 in this spot. And so technically, I mean, you could show the work here. If you just divide the middle by 2, the right side by 2, and the left side by 2, we get that x over 2 is in between pi and 0. Now our expression, 2 sine x over 2 equals 1, we're just going to isolate sine of x over 2 by dividing by 2. Okay, so divide out the 2 from the left and the right. Now the two numbers over our interval, notice our adjusted interval from 0 to pi with sine values of 1/2. So from 0 to pi on your unit circle, when is sine 1/2, and it's at pi over 6 and 5 pi over 6. Okay. And just a quick reminder, we're picking the radian values because we were given our interval in radian measure. If this was given in degrees, if this said 360, we would translate this to degrees. Okay, so x over 2 is pi over 6 and 5 pi over 6. It's not x because notice it was sine of x over 2. So we still have to find x. So we just times this left equation by 2. So we get 2 pi over 6, which simplifies to pi over 3. And this right equation by 2, so we get 10 pi over 6, which simplifies to 5 pi over 3. And so our solution set in the interval from 0 to 2 pi is pi over 3 and 5 pi over 3. Now part B says to find all the solutions, so we have to actually adjust our period of our function accordingly. So for sine bx, so in general, if you have sine of a number times x, so there's some number affecting your argument here, your period for sine is 2 pi over that number, 2 pi over b. So for us, we're working with sine of x over 2, so there's like an invisible 1 up here, so this is actually 1/2 times x. So our period is 2 pi over 1/2. b is 1/2. So when you flip and multiply, your period is actually 4. So normally the period for sine is pi, but based on this half angle we're working with, sine of x over 2, we had to adjust our period. So for our solution set, we have to add 4 pi n, or 4n pi. So multiples of 4 times pi to our original two answers, because the period, this function repeats every 4 pi, not every 2 pi, these function values. Next example, solve cosine 2x equals cosine x over the interval from 0 to 2 pi. Okay, Now, it might be tempting, and don't fall for it. You might think, oh, I'll just divide out a cosine x. You can't do that because cosine 2x is not twice cosine x. It's cosine of twice the angle of x. So it's a completely different value most of the time. It's not just 2 times cosine x. The 2 being after the word cosine is important. If the 2 was in front, it would be different, but it's right after cosine. So this is part of the angle. And so instead, we're going to use one of our identities, one of our double angle formulas from chapter 5. Cosine 2x we know is equal to 2 cosine squared x minus 1. So we replace the left side. And this is so that we can write everything in terms of just cosine x, no longer cosine 2x. Okay, now we have this quadratic equation. So we're going to bring over the cosine x by subtracting. And then you can factor this if possible. So see if you can. Think of this as y if it helps. This is like 2y squared minus y plus 1 equals 0. And so this one does factor. This would be like 2y plus 1 times y minus 1. Okay, so we have two factors that multiply to equal 0. So we set each factor to 0. So 2x plus 1 is 0, or cosine x minus 1 is 0. So we know if we solve for cosine x, it's negative 1/2 over here, and it's going to give us values on our unit circle from 0 to 2 pi of 2 pi over 3 and 4 pi over 3. They give us this cosine value of negative 1/2. Over here, cosine equal to 1 on our unit circle happens when x is 0. Okay, so those are going to be our solution set answers. 0, 2 pi over 3, and 4 pi over 3. In this example, we're going to solve 4 times sine theta times cosine theta equal to square root 3 over the interval from 0 to 360. So same interval we keep working with quite a bit, but this time it's in degree mode. Okay, so we are going to start factoring and isolating. This one's a little bit tricky because you sort of have to look at your identities. So what I would recommend is having a list of your identities you learned from chapter 5, double angle formulas, sum and difference formulas, half angle formulas. Just have that available as you're working on these problems, because that way you can kind of match up what you're given with one of the identities. And so the reason we want to factor out just 2 from the 4 is because of one of our identities. So our double angle formula for sine 2 theta, is 2 sine theta times cosine theta. So if we factor out just a 2 from the 4, it leaves the left side of this identity equation. So we can replace it with sine 2 theta. So what was in the parentheses is now sine 2 theta. Okay? And then let's divide out the 2 on the outside. And so from our given interval, we were given an interval, and this is always for your variable on its own. So this is for theta. So theta is between 0 and 360, but now we're working with sine of 2 theta. So you have to adjust this interval accordingly for what you're working with. So you basically just multiply everything by 2 here. So 0 times 2 is 0, theta times 2 is 2 theta, and 360 times 2 is 720. So we're looking for angles between 0 and 720. It's actually 2 full rotations on your unit circle. Okay. Now 2 theta has to equal these 4 values because of this sine value. So on your unit circle, sine equals 3 pi over 2 at 60 and 120 degrees. But if you rotate around your unit circle one more time, on second rotation to get you up to 720, you have 420, which was coterminal to 60 degrees, and 480, which is coterminal to 120 degrees. And then from here, you're going to solve for theta. So just divide everything by 2, because it was 2 theta, and then you end up getting 30, 60, 210, and 240. And so that is your solution set. Now let's continue the same example, but find all the solutions. So we just finished finding the solutions on one interval, and so now we're going to adjust that for all the solutions. So all angles 2 theta that are solutions to the equation we found are going to be found by adding multiples of 360 degrees to our basic solution angles 60 and 120. So these were the first 2 angle answers we got. before doing our second rotation around our unit circle. Okay? So we start with the fact that 2 theta equals 60 and 120 from our work, and then we add multiples of 360 to both of those answers individually. And then once you have these two equations, now you divide by the 2 to get theta. So when you divide by 2, you get theta is 30 plus 180 multiples, so n times 180, and 60 plus n times 180. So you want to take your original answers before you divide it by the 2, and then that's when you add the multiples of 360, then do the division, then divide by 2. Okay, so our solution set, where our period was adjusted for our function being 2 theta instead of just regular theta, is 30 degrees plus 180 n, 60 degrees plus 180 n. In this example, we're going to solve tangent 3x plus secant 3x equals 2 over the interval from 0 to 2 pi. So one way is to express everything in terms of secant. So we had another problem we tried just a little while ago where we had tangents and secants, and we expressed everything in terms of tangent. This time we're going to express everything in terms of secant. Okay, so here's our equation, and we're just going to isolate tangent 3x on the left by subtracting secant 3x, and then what you can do is square both sides here. And why we're going to square is very similar to the previous example we did with tangent and secant. It's because tangent and secant are related by one of the Pythagorean identities if you square them, if they're squared. So you're squaring both sides of your equation. So on the left side, be careful, it's just tangent 3x squared, and so we don't square the 3, it's just the angle is still 3x. So the square just goes on the tangent, so tangent squared 3x. On the right side though, you do have to FOIL this out because this is a binomial. So feel free to pause this if you want to work this out. You're doing 2 minus secant 3x times itself. Okay, after you worked it out, you got from FOILing 4 minus 4 secant 3x plus secant squared 3x. Okay. Now we use our Pythagorean identity to rewrite the tangent squared in terms of secant squared. So again, in a previous example, we rewrote the secant squared using tangent squared. This time we're doing the opposite. We're rewriting the tangent squared as secant squared minus 1. Okay? And then we're just going to simplify this expression. So we're going to bring like terms together and simplify. So if you simplify, you'll just get 4 secant 3x equals 5. And let me just walk you through it real quick. If you add the 1 over here, that's where the 5 came from. If you take this negative 4 secant 3x and you add it to the left side, that's why it's now positive. And then if you subtract secant squared 3x from both sides, it goes away. It adds up to 0. Alright, and so if you divide by 4, you get secant 3x is 5/4. And then we're going to use the fact that secant is the reciprocal of cosine. So if we flip this answer over, we can use cosine. So cosine 3x is 4 over 5. And then we're going to multiply each term of our interval by 3 to adjust for this angle being 3x. So x, we were told to find x between 0 and 2 pi, but we're working with 3x, so you're just going to take 0 and times it by 3. X times 3 gives you 3x, and then 2 pi times 3 gives you 6 pi. So you want answers between, or angles between 0 all the way up to 6 pi. So that's actually 3 full rotations on your unit circle. Alright, so using a calculator and the fact that cosine is positive in quadrants 1 and 4, because this is positive 4 over 5, so we get these answers. So 1, 2, 3, 4, 5, 6 answers. And 6 answers sort of make sense, hopefully, to you, because in one rotation of your unit circle, you have 2 answers, okay, because cosine is positive in 2 quadrants, 1 and 4, but then you keep going around your circle 2 more times for a total of 6 pi radians. So you get these 6 answers, and then this was 3x. This was for angle of 3x. So then divide all these answers by 3, and you get these 6 answers. Now we do have to check, because our work we squared, so we're going to take these answers, So we're going to check our answers using a calculator. And again, it's because we squared both sides of our equation, so we might have some extraneous solutions. Now, our original equation, if you look back at it, it was the right side equaled 2. So when you plug this into your calculator, and these are just views of the calculator screen, you're looking for answers that look like 2. Because we're using decimal approximations, it's going to not be exact, so you're looking for numbers that are pretty close to 2. They don't have to exactly be 2 because we're using decimal approximations. And so you notice 3 of these 6 answers are very, very close to 2. 1.999 happens when we plug in 0.2145. We get 2.00003 when we plug in 2.3089. And then we get out 2.00007 when we plug in 4.4033. The other 3 answers are not even close to 2. This is 0.5, 0.5, and 0.5. So our solution set is the 3 answers that actually gave us values close to 2. And 0.2145, 2.3, and 4.4.